There we go.
Okay, so yes, regarding the early universe and our belief or openness to inflation, we're we're trying to sort out what needs to be explained and what constitutes an explanation that we'll be satisfied
Hmm.
with. And there, as I was reading more of the literature that I haven't sent you all of yet, just to not,
Hmm.
because I would like you to do exactly what you're doing, which is to form your own thoughts about it first, right?
Hmm.
But just to bring you little snippets in, as I reread um, the discussions around inflation, and it's, I remember it because my professors, especially at Chicago, were a lot of the ones who built the inflation paradigm, and so
Hmm.
they were very enthusiastic about it, right?
Hmm.
And so
Hmm.
I remember their how they conveyed it, and that it's telling that I was rereading one of the papers, and it's something like, they're saying in some sense the goal is to be able to explain the current conditions, the flatness that let's just pick, or sorry, let's just pick the homogeneity and the isotropy.
Hmm.
So the horizon problem to explain why things look the same in regions that would not have been in contact when their light left us. They're really focused on wanting to be able to explain it by some mechanism that would make it that way, regardless of how it was initially. And
Hmm.
I think that's significant, right? And it's related to
Yeah.
Penrose's comment there, right? Because they're basically wanting to assume that, well, the universe could have been anything. Different regions could have been very different, and all kinds of stuff could have been going on. We want a mechanism that will homogenize things regardless of the initial conditions because we don't want to have special initial conditions, right? And that's
Hmm.
a
Hmm.
that's a perfectly valid goal, but
Yeah.
it's really important to be upfront about that as your goal
Hmm.
because I think, and that's what it was. This bothered me when I was thinking about it when I was your age for the first time, and it bothers me. As you can tell, it was fun to rediscover this essay from 10 years ago because I was like,
Hmm.
clearly it bothered me then,
Yeah.
and it bothers me even more sharply now, which is I don't know, sorry, too many sidebars, but I
Hmm.
think I think one of the things that's going to be really useful in our paper is actually to do a parallel analysis of a static universe
Hmm.
in the same way that we kind of did with
Hmm.
the AJP paper,
Hmm.
because I think it'll help clarify some of the issues if we get the expansion
Yeah.
part out of it, we can just
Uh-huh.
so for example, if I imagine 13.8 billion years ago that an unbounded but flat universe comes into existence and it's static,
Hmm.
I'm not sure that I have any bias at all toward thinking that different regions should have dramatically different temperatures. Like whatever brought
Hmm.
this into existence, I almost feel like it would be more natural for it to be uniform than for it not to be, because
Hmm.
whatever brought it into existence is is going to happen somewhat universally, right? I mean, even I think we talked about this before, but the fact that the laws are the same everywhere already means there
Hmm.
was a kind of an unbiased sameness about the
Hmm.
different
Hmm.
regions when it started. So,
Yeah, I was just gonna say it's kind of like um we're imagining like I don't know, the image that pops into my head is just kind of having like a mixing bowl of like hot, dense early universe
mhm,
and then having like the space time and then just kind of like what I feel like what maybe everyone else is thinking about is like, oh, the Big Bang is like, it got poured out into the space time. And so now all of the temperatures and stuff need to like reequilibrate, and it needs to like get used to like the space time around it, and like it needs to like settle first. But like space time and the contents of the dense early universe were together the whole time. And so it's
Right.
like what, and I mean, with that much energy in that small amount of space, like maybe it's hard, that small amount of space and time is hard to maybe imagine there being like, I guess maybe associating the chaos of how much energy there is in a small amount of space time
Right.
is like, it's hard to think that it could just be like uniform and calm, because that's not usually associated with like high energy and chaotic environments, I guess.
Right. 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 You expect, yeah, that's good. You sort of expect that there would be fluctuations that would make things different.
Hmm.
But yeah, that's an interesting point. Okay. Yeah, yeah, yeah. I want to think more about that. Um, right. Would fluctuations at some point, just because there's so much energy available, just the statistics of it kind of, right? That
Hmm.
like if you have a lot of energy, then there's going to be a sort of a root mean square, you know,
Hmm.
variation kind of.
And I
Hmm.
mean, I guess maybe I think my brain is still confused about this concept, which is why I'm bringing it into the conversation.
Yeah.
But like, the idea of black holes being, a region of space-time where within a certain radius, the gravitational influence is so intense that light can escape. It could be like a matter of like scale, I guess.
Okay.
Like, I don't know, one time, I can't, not one time, a few times, because we talked about it, I was confused. And then I think we still keep talking about it because I think I'm still suddenly confused about it. But
Is that right?
like when we had our um static universe model, like we couldn't just say like, oh, I'm just going to make the radius the entire universe. And so the contents of that radius is so gravitationally intense. Why isn't our whole universe like a black hole, kind of thing?
Right. Right.
So
A-
I guess that idea is kind of spilling into this early universe. Like maybe it's a matter of scale that people are getting confused about.
Good. Yeah. And it's you're right to express confusion about that because it's a non-intuitive idea, I think, and there's a lot of pieces to it. I'm still unpacking it too. But
Hmm.
I think the key idea is that all the intuition we've built about about black holes in the static case is built around um, ironically, essentially not fully embracing general relativity because we're not
Hmm.
using the Einstein equations,
Right.
right, to relate space-time curvature to energy density. So, I
Hmm.
mean, but basically the idea is that like if you can sort of look at the Friedman equation and see that if you have a uniform energy density, it's not going to be static.
Hmm.
If you have a uniform non-zero energy density, the Friedman equation doesn't allow it to be static because basically, R dot over R is proportional to the square root of rho.
Hmm.
So if rho is zero, then R dot is zero
Hmm.
and you get static. But if uniformly rho is not zero, then the space is going to be expanding or contracting. And so you can't, so I think that's the intuitive conceptual idea to sort of hold on to as your anchor is that um, you can't basically in our static model, we're saying, well, if I have a big region with a lot of stuff in it, it's going to collapse
Hmm.
into a black hole of a certain radius. In the full general relativity model, if I have a uniform region like that, I have to, the whole region has to obey the Friedman equation. And so
Hmm.
even though the Schwarzschild criterion might say that it's going to collapse, it might not because the whole space is going to be expanding.
Right.
You see what I mean? And
So, I
and
mean,
so that fights the collapse. And so that's
yeah,
that's
right.
where like
Okay.
you need a little pocket where the density is significantly higher, and that's why the delta
Hmm.
rho over rho comes into play, not just the
Hmm.
rho like in ours.
Right.
And then and in a way we're doing a delta rho. We're letting rho be the delta rho because we're assuming there's this big region where the density is rho and everywhere else it's
Hmm.
zero. And so our
Hmm.
that's our delta, right?
Hmm.
But and so that's why remember when I had the revelation one time when we were talking fairly recently, a month or two ago. Well, it was around the time we submitted our paper, so it must have been like
Hmm.
late December, early January,
Hmm.
where I had the revelation that, oh, if we're going to do this, we do need the Friedman equation, but K is definitely not zero now in this little local pocket, right? To make a black hole, you have to have a situation where K is not zero,
Hmm. Yeah,
right?
because the black hole itself is not
Because it's curved. It's like
gonna,
it's
yeah,
closed.
it's not gonna
You're
be
making a
flat.
little pocket universe that's closed, not flat
Hmm.
or open. Yeah.
Hmm. Hmm.
And so, and I found some papers that made mention of that enough to make me think that that's the right way to think about it.
Okay.
Basically the density, it's
Yeah.
over dense for the
Hmm.
for the amount of expand. Yeah, that's a good way to think of it. So if you look at the Friedman equation with k equals zero, it basically tells you that r dot over r squared. So essentially the rate of change of r is related to rho, right?
Hmm.
But that's only if k is zero. If let's see, how do I want to say this? Yeah, to make it flat for a given rho, you fix your r dot, right?
Okay.
Because if you write
Yeah.
down or just think in your head, picture the Friedman equation the way we've been looking at it, right? I don't
Hmm.
know if there's too much glare to see that if I do that.
Yeah, I think that's a bit too much glare.
Yeah. Okay. But you're right. I mean, it's just r dot over r squared equals 8
Yeah.
thirds pi g rho, right?
Hmm.
So the reason there's no k term in there is because I set it equal to zero. But
Hmm.
by setting k equal to zero, I've made it so that how r changes quantitatively is basically equal to how much density there is,
Hmm.
right?
Hmm.
If whereas if I have a situation where rho is big, right? So what if I had a situation where 8 thirds pi g rho is much bigger than r dot over r squared? Then I'm going to end up, I think, with it
Gravitationally
collapsing.
collapsing. Yeah.
But to do that, to make rho much bigger than r dot over r squared, I need another term in my Friedmann equation, and
Hmm.
that's the curvature term.
I see.
So maybe a summary way to say it is if the density is big enough to make it closed for the given expansion rate that you have,
Hmm.
then K will be positive.
Hmm. Hmm. Yep, that makes sense.
On the other hand, if R dot is too big for the amount of rho that you have, then K will be negative because then it's
Hmm.
going to be open.
Right.
The special case where K is zero is the one where R dot over R squared is actually equal to a thirds pi g rho. So it's, in the Newtonian sense, it's like the difference between I can I can throw a ball in the air and look at its current velocity and compare that to the mass of the Earth and how far it is from the Earth. That's like our
Hmm.
rho. There's three possibilities qualitatively, right? Either it's going to turn around and fall back. That's
Hmm.
the K positive case. It's going to just barely sort of, as it approaches infinity, slow down to zero velocity. That's the K equals zero case. That's flat.
Hmm.
Or it's going to fly away and never come back. And that's the
Hmm.
open case, or K is negative.
Right.
Yeah. So
Yeah.
in the local, so basically what we're doing, this is good prep for your future. What you're doing in the in the full treatment of density perturbations to think about whether they form black holes is you're basically asking, am I making little pocket universes where the delta rho, the overdensity compared to the background density, is going to be enough to make a little
Hmm.
pocket universe with a positive K on a certain scale that will collapse. And then from the point of view of someone outside of that region, that overdense region is going to collapse to form a black hole.
Right.
And
I
then
think it's
that's
like
where, yeah.
like the certain scale. Like I know that R is the scale factor. I know that dr dt is like this expansion that's happening.
Yep.
But it's just like I think I'm having trouble understanding what R is.
Yeah, R is the way of parameterizing the the change of the distance scales. It's the copier, it's the photocopier enlargement factor. Yeah.
So like
If I put a piece of graph paper and that's my standard scale, and I put it on a
hmm.
copier and I say I want to enlarge it by a factor of two, that would be like saying
Hmm.
R is two,
Hmm.
because then everything's going to blow up by that same factor.
Right. And so then the change in R is like it blowing up
Right,
to that scale
right.
factor.
And it's key, and this is part of the confusion, I think. It's key that the only reason you can do that, which of course we're destroying by trying to talk about perturbations, so this is why it's delicate.
Hmm.
The only reason you can do that with a single parameter R is because it's homogeneous and isotropic, right? So what you're really doing is the Einstein field equations, right? You're saying,
Hmm.
how does space-time respond to the distribution of matter and energy? And we're saying that because there's so much symmetry involved, the Friedmann equation is a huge simplification of the
Right.
Einstein
I'll
field
put some
equations, right? Where it's like a 10 by, 10 dimensional tensor or whatever. I forget how many elements are in it now that I think about it. But you can picture the tensor, a g mu nu equals t mu nu, some
hmm.
constants. So we're just throwing away almost all of the details upon the assumption that I only need one. It's like when we're doing an integral in Calc 2 or something, right? And if you have spherical symmetry, then you can parameterize it with just an r and a theta.
Mm-hmm.
And then in
Mm-hmm.
fact, if
Be
you don't
super
even really need the theta because everything's this at all values of theta, everything looks the same. So the only thing that
Mm-hmm.
changes is r. So we're
Mm-hmm.
doing the same kind of thing. We're saying that what should be several terms is now being reduced to only one variable because of the
Right.
symmetry,
Right. Which is R.
which is R or A. I
Okay.
mean, a lot of people call it A in
Mm-hmm.
the
Mm-hmm.
literature, but it looks like acceleration, so I tend not to do it.
That's funny. Okay. Yeah. So then when you say like a black hole at a certain scale is folding in on itself because it has a positive K, like that certain scale is just like, one if it's today, or, you know, between 0 and 1 if it's.
Yeah, yeah, sort of. I mean, I guess there's another meaning to the term scale in that sense, which is at a given moment in time with a scale factor of whatever it is, a half or one or whatever,
Mhm.
then you can talk about a distance, a length scale
I see. Okay.
that is the scale on which, that's people normally, that's probably part of the reason why they do that. People talk about it in terms of the wave number, right? They Fourier analyze it.
Mm.
So rather than
Hmm.
actually talking about a length scale, they talk about the power spectrum in,
I see.
right? Like where K now is the wave number,
Hmm.
like essentially the wavelength. What is it? Two pi over the wavelength, I think is the wave number.
Hmm.
Look at the
That sounds right.
yeah, because it's
Something
like
like that.
frequency, right? It's like
Hmm.
frequency for distance. So it's it's the length scale. So now I'm mean scale in a different sense. That's a good
Hmm.
question. Now I don't mean the scale factor. Now I mean um, uh, what's the length scale of the perturbation that I'm talking about, right? So people talk about it in terms of like
Okay.
sound waves. There's like vibrations on different,
Hmm.
like normal nodes on a guitar string or whatever,
Hmm.
right? You could talk about if I pluck a guitar string with a certain wavelength wave, then the amplitude fluctuations of the guitar string have a length scale to them that is roughly
Hmm.
the wavelength of whatever wave I've generated. And
Hmm.
so when I do it in Fourier space, how much power is in a particular wavelength is sort of an indication of what the length scale is, where there's big fluctuations in density.
Hmm. Hmm.
And that's what's going to determine whether something, on that region, you have a part of the universe behaving differently, where you can sort of do a little mini analysis of it. What I mean? Like if you assume the fluctuation is symmetrical, spherically
Hmm.
symmetrical, you can almost treat it like there's a little mini universe within the bigger universe
Hmm.
that has its own density, which is higher than the background density. And then if the expansion rate is still sort of the average expansion rate, then that means that's going to collapse out of the background.
Hmm.
That kind of makes sense. So
Yeah.
this is why I made such a big deal about us doing the static case first. It's
Hmm.
because you're really doing the same kind of analysis that we did for the static one, which is that we're looking at a background uniform space and thinking, well, what if I get a clump? On what sort of length scale is a clump going to collapse?
Hmm.
Now I'm just doing the same thing, except there's an extra factor going on, which is that the whole space I'm doing this in is expanding. And so
Hmm.
and so this is how Hawking did it in his paper, right? Is just
Hmm.
treating it as well. So now you've got some competition. It's trying to
Hmm.
collapse, but you've also got some sort of kinetic energy from the expansion
Hmm.
that's trying to pull it apart. And so
Hmm.
it's the same it's the same thought process about how you're forming structure, but the details are different because now you've actually got something that something that would have collapsed in a static space won't actually collapse in a expanding space because the expansion will
Mhm.
just carry it along
Mhm.
and actually pull it
Mhm.
apart.
Mhm.
So there's a different threshold for forming structures in an expanding
Right.
space than in a static one, is the sort of
Right.
conceptual framework.
So like for inflation, the expansion rate is so fast that it makes it so nothing can collapse, but
Right.
everything is eventually like, uniform and meets the
Right.
criteria that
Within right, right, right. So within a certain region, so what inflation does is it postulates that there was a period of time where that rho term in the Friedman equation was constant for some amount of time
Mhm.
and doesn't vary as R, as R expands, the density doesn't go down.
Mhm.
And it turns out that when you put that into the equation, then that's what gives you an exponential, you know, instead of R being T to the 1/2 or T to the 2/3, like it is for matter or radiation dominated regions,
Mhm. It's
R
e to
becomes
the
E to the power T times something.
Mhm. Mhm.
And so that means that depending on what the constant is in the exponential expansion, you can very quickly end up with R that was, whatever, R that was one. Well, usually the way people do it, it'd be like R that was one, R that was 10 to the minus 30 suddenly becomes R is only zero point 0.1 or something, right? And so
Mhm.
that means that if you're actually looking at some structure that suddenly that had some big variations in it, suddenly fractionally it's very, very smooth or
Mhm.
very flat or however you want to think about it, right?
Mhm.
And
Right.
it takes things, and the key thing for the horizon problem is it takes things that were very, very close together and makes them very far apart.
Mhm.
So, the essence of the horizon problem is we're basically saying, oh, look, I see these 2 points in space. If I extrapolate back in time to to how old the universe was when the light left from those regions, the universe was very young, and so there hadn't been time for those two things to communicate, and that's the horizon problem.
Mhm.
But with inflation, it says, well, actually, you didn't know about this little bit at the very beginning. You know,
Mhm.
they were actually so. I mean, I guess the intuitive sort of idea it would be like if you saw two people walking apart and you assumed they'd been walking apart at the same rate. And so you assumed that a certain amount of time ago they were a certain distance away from each other. But you didn't know that actually for the first 10 seconds, they were actually moving apart at millions of times faster than what they're doing now. And so actually they were way, way closer together for the first few seconds
Mhm.
than what you assumed.
Mhm.
And so they had time to pass messages back and forth because they were in range to pass messages back and forth when you assumed they were actually in different states or whatever,
Right.
because you assumed that they were moving at the same rate as you see them moving now, or at least
Mhm.
comparable to what they're moving now.
Mhm.
So that's the idea. So in fact, that brings me to I know we're about to run out of time for now, but I was actually going to
Mhm.
suggest that for something for you to think about
Mhm.
is just to try to understand the horizon problem. Let's see if I can very quickly share my screen here. Um, uh, Try to understand the horizon problem totally from a static um,
Mm,
situation, just to build your intuition about what it means. And I'll show you what I mean with a drawing here. I think this would be a really useful thing to just sort of play around with. Um, you can see my screen, yeah?
yeah. Hmm.
Okay. So, right, so I drew this as a so it's totally static case. And the idea here is that, um, right, so this axis is space, like we usually do the space-time diagram, right? And this one's time.
Hmm. Hmm.
So space is a one-dimensional line that little ants live on, and
Hmm.
time goes forward. So here's the idea is, so see how I've labeled a T1 on there?
Hmm.
So that's a slice of space at time T1 that is, you know, that much times after the beginning. So I'm assuming that my universe came into existence here.
Hmm.
Okay. So I call that TB. T1 is like T beginning. T1 is
Hmm.
like when something happened, like the cosmic microwave background. So you could think of this as being, for example, this could be what would that be? 380,000 years after the beginning. So that's when the microwave background got released. So
Hmm.
you could say that that's T1. Okay. So I drew this so like a usual space-time diagram where that these are in units of CT along here, and this is time. So, or sorry,
Hmm.
time should be in CT. So
Hmm.
it's all in meters or whatever you like. And so
Yeah.
so the um, light travels at a 45-degree angle, right? And
Hmm.
remember that from relativity? Like if I,
Yeah.
if I make space in meters and time in meters, then light travels 1 meter of time per meter of
Hmm. So it's
distance,
like a
right?
constant
With it.
velocity
So the
kind of
constant
thing.
velocity is actually a 45-degree slope,
Hmm.
right? It wouldn't, just all that would happen if I changed the units is that it would be much steeper or shallower or whatever.
Hmm.
Okay. So that means that if I take a spot here that, radiates out in the two directions that it has available in its line universe, then when I'm here with my eye or my telescope, radio telescope actually, right? And I'm looking at the cosmic microwave background and I see that lovely image of the, early universe that we all know
Hmm.
and love now, right? The little spotted
Hmm.
thing of the cosmic microwave background. When I say I'm seeing a particular spot on there, what I mean is that spot when the universe was this old, that spot happened to be radiating in such a way that I'm seeing it now,
Hmm.
right?
Hmm.
And I can also look over here and see a similar spot over from this direction that I would also just be seeing now, right?
Hmm.
So this distance is the separation at which I can see different spots. Yeah. And I noticed that, this spot is about the same temperature as this spot over here,
Hmm.
which is no big deal because they sent their light to me, and it's perfectly fine that those widely separated regions, they've had this much time for their light to travel, and so there's been plenty of time for light from widely separated regions to get to me.
Hmm.
The issue is the comparison between how big this time is and hence how big this distance is with how far this is when it was emitted from the beginning of the universe. Right? So essentially, what we're doing is we're comparing this time, which is short, to this time, which is long.
Hmm.
And so that's what creates the horizon problem because now I can look at this and I made this drawing here to say this is as far as anybody could have communicated between the beginning of the universe and the time when the cosmic microwave background light left. So this is the length scale in a static universe over which I would expect physical processes to be able to take, like if this region was hot and this
Hmm.
region was cold,
Hmm.
that's how long, like only on lengths smaller than this has there been enough time to equalize them, right? Because anything bigger, if I had a hot spot over here and a cold spot over here, well, they haven't had time up to here to communicate,
Hmm.
to like send pressure waves or whatever, or send notes to say wear your blue shirt today or whatever, whatever the,
Hmm.
right? So
Right.
that's the essence of the horizon problem in a static universe. That would, like that would be exactly the horizon problem. If we saw stuff that looked uniform on these kind of scales from a
Hmm.
time back here, and we knew that the universe began only a little bit before there, we would say, well, if I assume that the universe should have started out of equilibrium, which is a big if,
Hmm.
then
Hmm.
I have no way for it to have gotten in equilibrium.
Right. There wasn't enough time
There
yet.
wasn't enough time for physical processes to do it. Given, and a key to this is the speed of light limit, right? I'm assuming that there's a
Hmm.
speed of light limit. So then here's where inflation comes in. I can sort of turn this quickly into an expanding universe. Is, well, yeah, these 2 points were, sorry, this point and this point were not close together
Hmm.
back then. But if I say that, well, actually, there was a little region of time in here where it actually wasn't static, but it expanded like a balloon, right?
Hmm.
See what I mean?
Hmm.
Then
Yeah.
then these regions that were close together and had time to share information, little tiny regions that were very close together, now when they get
Hmm.
here are very, very far apart.
Yeah.
So that's one way of explaining. But it's worth drawing this all out for yourself and basically just, you know, explaining to Riley or whatever, like what is the horizon problem in a
Hmm.
static universe so that you really have a solid grip on that. Because then you can start to back your way into, okay, well, how does expansion help with that situation?
Hmm.
And you can start questioning your assumptions like, okay, but the only reason there's an issue is because I assumed that these regions were different when space got created and they needed
Yeah.
to be equalized. And I want to think more about your point about the if it was hot at the beginning, would there have
Less
been just,
bad.
even if it was equal, would there have been just fluctuations from I think that's a valid point to consider. Anyway,
Right. Because I mean, that's kind of where um, the like primordial black hole idea kind of came from as well. Like because there was just so many, like because there was so much energy and the possibility for there to be a lot of like perturbations and pockets of really large densities
yes,
where like primordial black holes could form.
yes, yes, right.
Okay. I need to find this link that I need to go to
Yeah, 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 you should go.
for the
So,
next thing.
so play around with that a little bit, just see what
I
thoughts come up,
will.
and then we'll just check in and figure out when to meet next.
I'm
Okay.
excited. Thank you so much,
This is
Todd.
fun. Yeah, yeah, yeah.
This is
Okay, have
cool.
fun.
All right. Thank you.
Yeah, see
Bye.
you later, Logan. Bye.